Hi everyone, so today we're going to continue our Foundation Mastery Method series, and we're going to be talking about algebra and geometry. So there's some interesting concepts and formulas that we can learn. We're going to learn more about these formulas and what they mean and how you can use them to solve various kinds of problems. Okay, so to start off, let's say you have a circle and you make two chords from one part of the circumference to the other, and the angle between the two is x. Next we have a arch, which is S, and the angle x is between C, A, and B, right? So we want to find the relation between S and x, and the relation is as follows. We can say that the length of x in degrees is twice the value of x. So if x is 30 degrees, then the value of s in terms of the angle is 60. So this is one formula that we can use. A similar formula is, let's say we have the same angle x between two chords, and then we have our center D, right? And then we form another angle that is around the center. And now we want to find the relation between s and x, but with respect to the center, and the central angle is y. The relation we get is s is equal to 2x, which is also the same as y, and so we can say s equals y equals 2x. So if you know one angle from that, you can easily find the angle about the center as well as the length of this arc. Moving on, if you inscribe any quadrilateral inside a circle, the relation between the angles is that opposite angles are supplementary, meaning x plus y equals 180 and m plus n also equals 180. So if you know either the value of x or y, you can find the other simply by subtracting them from 180. Another property is for external angles. So let's say we have an angle x that is outside the circle, formed by two chords that begin inside. And once again, we have an arch S2, and then we also have an arch S1. Right? So the formula to find x is simply 1/2 of s2 minus s1. Now if we notice and we look at our first relation, we can say here that s2 minus s1 is basically 2x, right? And so if we substitute that with 2x, the 2's would cancel out and we would be left with x. So we essentially derive this relation from the first one. Another relation we can derive is for the length of the sides. So let's say the length of this part outside the circle is m1 and the part inside the circle is m2. Similarly, we have n1 and n2. Then we can say that m1 times m1 plus m2 equals n1 times n1 plus n2. So this is a relation for the sides, and then the relation below is for the angle. Lastly, we have another example where we have two intersecting chords, and we have the sides m1, m2, n1, and n2, and we can say that m1 times m2 equals n1 times n2. So this is another relation that we can use in order to derive values if we know one or two of those values. So now let's do a few examples based off of what we learned. So let's say we have this example here where you've been given S1, S2, and S3, and you want to find the value of x. So recall the formula we learned before about x being 1/2 of s2 minus s1. So we simply use that formula here and we substitute the values of s2 and s1, and we get that x equals 15 degrees, right? Additionally, if we want to find the value of s4, that's fairly straightforward. So we know that all the angles of a circle together equate to 360, and so s4 would simply be 360 minus the sum of the other three angles, and if you calculate that, you would get 231, and you can verify that yourself. Another example here is you want to find the value of m. So recall the formula we learned about m1 times m1 plus m2 equals n1 times n1 plus n2. So here our values are 8, 6, 4 and m. And so if we use the formula and we equate them to each other, we find that m equals 10. So we were able to use the formula we learned previously to solve this question. Now we have a question that builds off of the previous question. So if we notice, it's fairly similar, except that this chord here doesn't extend all the way inside the circle. So this might look very complicated, but the only difference here is that our m2 is essentially 0 because there is nothing inside the circle. So taking m2 to be 0, we can use the formula and derive m to be 6. Okay, now we're going to learn about patterns and parity. Okay, so let's say we have this sequence 0, 2, 5, 9, 14, and then what comes after? So it's kind of difficult to observe a pattern right off the bat. So let's look at a couple of shapes here. Okay, so we have a triangle. A triangle has 3 sides, right? And then we have a rectangle which has 4 sides, and then we have a pentagon with 5 sides, right? So for the triangle, if we notice, it has 0 diagonals. Recall that a diagonal is a line segment that joins 2 opposite corners, so that's really not possible for a triangle. Let's go to a rectangle now, and we notice that there are 2 diagonals that can be formed. Similarly, for the pentagon, you can choose any corner. So I will choose the corner at the top, and then you can make 2 chords from there. And then you can choose any one of the corners on the sides, and you can make another 2 diagonals from there. And then lastly, we can choose the corner that is remaining, and we can make 1 more diagonal. So we get a total of 5 diagonals. And so if you look closely, the number of diagonals corresponds to the sequence that we're looking at. So to write this out more generally, if we notice the number of sides of a triangle and the diagonals, we can observe a pattern here. So the difference between the number of diagonals for each subsequent shape, it differs by consecutive natural numbers, right? So the first difference is 0 plus 2 equals 2, and then 2 plus 3 equals 5, 5 plus 4 equals 9. So we notice that each time the diagonal is the previous diagonal plus the natural number, right? And so we can further confirm this as a mental exercise. If you want to see what comes next, it would have to be 14 plus 6, which is 20. So let's see if that's true, right? So here we have a 1, 2, 3, 4, 5, 6. Okay, so we have a hexagon, right? And we notice that it has 9 diagonals. Now we have a heptagon, and that has 7 sides, and if we were to make the number of diagonals from each corner, we notice that we have 20, which conforms to the pattern that we observed above, right? Similarly, if we have an octagon, we can find the number of diagonals, and we see that this pattern holds true for any number of sides. And so this is how we were able to identify the pattern. Now to generalize this and get a general formula, we can say that the number of diagonals is s times s minus 3 over 2, where s is the number of sides. And so if you want to confirm this, you can see that for the triangle, this would just become 3 times 3 minus 3 over 2, which is 0, and so on for the rest of the shape.